Junos OS Traffic Processing and Software Evolution module. By the end of this module, you should be able to describe traffic processing and evolution of Junos OS. Transit traffic consists of all traffic that enters an ingress network port, is compared against the forwarding table entries, and is finally forwarded out an egress network port toward its destination. A forwarding table, also known as Forwarding Information Base or FIB entry for a destination, must exist for a device running Junos OS to successfully forward transit traffic to that destination. Transit traffic passes through the forwarding plane only and is never sent to or processed by the control plane. By processing transit traffic only through the forwarding plane, platforms running Junos OS can achieve predictably high performance rates. Transit traffic can be both unicast and multicast traffic. Unicast transit traffic enters one ingress port and is transmitted out exactly one egress port toward its destination. Although multicast transit traffic also enters the transit device through a single ingress port, it can be replicated and sent out multiple egress ports depending on the number of multicast receivers and the network environment. Unlike transit traffic, exception traffic does not pass through the local device, but rather requires some form of special handling. Examples of exception traffic include packets addressed to the chassis, such as routing protocol updates, telnet and SSH sessions, pings, trace routes, and replies to traffic sourced from the routing engine. IP packets with the IP options field set. The options field in the packet's IP header is rarely seen, but the packet forwarding engine, or PFE, was purposely designed to not handle IP options. Packets with IP options must be sent to the routing engine for processing. Internet Control Message Protocol, or ICMP messages. ICMP messages are sent to the packet's source to report various error conditions and to respond to ping requests. One example of an ICMP error is a destination unreachable error, which is sent when no entry is present in the forwarding table for the packet's destination address. A second example of an ICMP error is a time to live or TTL expired message, which is sent when a packet's TTL is decremented to 0. In most cases, the PFE process handles the generation of ICMP messages. The Junos OS sends all exception traffic destined for the routing engine over the internal link that connects the control and forwarding planes. The Junos OS rate limits exception traffic traversing the internal link to protect the routing engine from denial of service or DOS attacks. During times of congestion, Junos OS gives preference to the local and control traffic destined for the routing engine. The Junos OS has evolved over time. It has existed in 4 different architectural forms. Junos OS started out as a single entity. In traditional Junos OS, the control plane, the forwarding engine, and all of the hardware drivers are modularized components of a single image. This software image is tightly bound to its underlying hardware. Virtualized Junos OS takes advantage of virtualization technologies to run Junos OS in a virtual machine, or VM, on top of the kernel-based virtual machine, or KVM, or VMware hypervisor. Note that all the components of Junos OS are still fused into a single image. The virtual SRX or VSRX and virtual MX or VMX products are examples of virtualized Junos OS. Further development of Junos OS took the advantage of virtualization further and separated the packet forwarding engine software and platform-specific components from the core operating system. The control plane and the daemons attached to the control plane remained with the FreeBSD kernel, but the operating system was opened up to external APIs, and the packet forwarding engine and platform-specific software was no longer directly embedded in the operating system. Disaggregated Junos OS separated the platform drivers and the forwarding engine, packet forwarding engine software, and is running them in their own virtual environments directly on top of Linux. The NFX series devices use disaggregated Junos OS. This disaggregation brings a number of advantages. Removing the platform drivers and forwarding engine from the control plane image and running them in another thread improves the control plane performance significantly. The Junos OS virtual machine is now hardware independent and focused only on the control plane, speeding up the innovation process. Linux is a multi-threading OS. CPUs are multi-core. The disaggregated Junos OS architecture permits Junos OS to pin software to different processor cores, and third-party binaries or other applications can make use of additional CPU cores. Unified In-Service Software Upgrade, or ISSU, is facilitated. Different versions of Junos OS can run in separate virtual machines. The virtualization infrastructure permits users to install third-party applications and tools on supported switching, routing, and security platforms. The last stage of evolution of Junos OS follows the trend of cloud computing, where systems leverage pools of hardware to perform tasks. This is the core concept of Junos OS Evolved. With Junos OS Evolved, the legacy FreeBSD kernel is removed. Because the core functions of legacy Junos OS were attached to the kernel directly as software daemons, the daemon processes have been redesigned to run independently of the kernel. In other words, they have been rebuilt as applications, independent from the underlying kernel, but are based on the same functionality and code concepts of the original daemons. In legacy Junos OS, information related to a daemon is managed, modified, and stored by the respective daemon. When that daemon experiences a fault or a restart, the information it manages and stores is lost, unless a system is implemented to run a backup of the daemon, which tries to synchronize its information with the primary daemon. This type of hot standby is inefficient and difficult to manage. With Junos OS Evolved, the applications that perform functions no longer store the information they process internally to the application. The application is a consumer or publisher of information. Information is sent to the application. It processes the information according to its design and publishes the results to a centralized, distributed database, much like a data center environment. If an application experiences a fault or is restarted, the new instance of the application retrieves the state information that the previous instance of the application had stored in the database, and the information is not lost. Because the functions of Junos OS Evolved are application-based and run on a Linux hypervisor, third-party applications that are developed to run on the hypervisor can be implemented as well. And because the information related to all processes on the device are stored in a distributed state infrastructure or database, third-party applications can be developed as consumers of that state information, which retrieve information from the data store for administrators, management platforms, and so forth. They can also be developed and implemented as publishers of information, which can publish information into the data store as long as it is formatted properly and utilizes the built-in APIs. Junos OS devices do not support the new Linux kernel or the distributed processing capabilities required to run Junos OS Evolved. Currently, Junos OS Evolved is planned for the cloud domain-oriented platforms, such as QFX and PTX series devices. Eventually, all new Juniper hardware can support Junos OS Evolved.